Okay, so I start this part. I think it's working, right? So here we have uh, shear stress. Shear stress, right? Shear stress. Then we want to find some direction. See, one arbitrary plane normal. The traction vector has the simple expression. The shear stress on this plane becomes this, right? Adding a constant and using, see, this is a little bit ab, uh, abrupt. Abrupt, I don't think. This is like too sudden. I don't know how to say in English. Maybe I can look up. Abrupt. See, this is actually zero. This part is zero. Right? So the funny thing, this F is just exactly S square. This function becomes stationary when something is equal to zero. This way, we obtain the three equations. We can obtain three equations. Maybe I skip the detailed calculation, but we just take partial derivative with respect to n1, n2, and n3. Okay. So here h is defined as summation. We may verify that three solutions of these equations are 0, and the value of the stationary shear stresses for these three cases respectively are. This is hard. I still don't understand. I think it's hard to understand from this text. So what is this mean? Maybe I can ask. So you can go to the next section. Okay, we try to go to the next section. Hydrostatic pressure and deviatoric deviator deviatoric stress. Deviatoric. What is deviatoric? Deviatoric. Deviatoric stress. 직사오력. 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 Hydrostatic pressure and deviatoric stresses. It is known that many materials respond differently to hydrostatic pressure than to shear stresses. When the normal stresses on the faces of infinitesimal cube differ from each other, the hydrostatic pressure is defined as minus P equal 1/3 sigma II 1/3 sigma 1 plus sigma 2 plus sigma 3. If we remove the hydrostatic part from the stress tensor, what remains is called the deviatoric stress S. S equals sigma II plus P delta Ij sigma Ij minus 1/3 sigma Kk delta Ij. There are material. See, this explanation is too simple, I think, here. It is known that many materials respond differently. Yeah, it's okay. hydrostatic part from the stress tensor. It is called deviatoric stress. deviatoric stress S. 직사오력. Deviatoric stresses is 직사오력. There are materials that respond not only to the stress but also to the rate of change of stress in time. Rate of change of stress in time. For a stress rate to be an admissible variable in a constitutive law, it has to be objective, frame indifferent. The obvious candidates such as partial sigma ij partial t and d sigma ij dt can be ruled out if we use the appropriate rate of the relation. When the rotation matrix Q is time dependent, the apparent rate of change in stress is best illustrated if we consider a bar under constant stress sigma 0 if we use a rotating frame with the x1 axis along the axis of the bar at time t equals 0. The frame shows sigma 11 equals sigma 0. As the frame rotates, we see sigma 11 diminishing, and eventually, after 19-degree rotation, sigma 22 has the value sigma 0. During all this time, the bar itself did not experience any change in stress. As it happens, an objective stress rate is not unique. A number of candidates have been proposed by various authors. A stress rate introduced by German in 1911, which is called the German stress rate or corrotational stress rate, appears often in constitutive relations. The physical meaning of objective stress rate may be explored in the following way. At an arbitrary point P in continuum, let us establish the origin of two coordinate systems, one in Eulerian system with unit vector EI and coordinates xi, and the second, a rotating system with unit vectors EI prime and coordinate xi prime at time t. The two systems overlap. We assume the second system rotates with an angular velocity omega. We will select omega later. Our goal is to compute the time rate of change of quantities from the point of view of an observer sitting on the rotating system in an incremental time delta t, the base vectors of the rotating system are related to those of the fixed system as something like this, where P is the orthogonal matrix. When T prime equal T, the system coincide and this. The time rate of change, the base vectors ei prime can be expressed as something like this, where W is we find this. From this, we observe that the spin tensor is related to P dot in the form when T prime equal T plus delta T, something like that. Any second rank tensor field Aij that is time dependent has components Aij prime T plus delta T in the rotating system. We define its rate of change as observed in the rotating system as like this. As the two coordinate system coincide at time t, now Aij at t plus delta t is given by this. Using transformation of coordinates and neglecting quadratic terms in delta t, we obtain this. Having the relation expression for the rate of change in a tensor in a rotating coordinate system, we would like to see how this quantity transforms under arbitrary time-dependence rotation q, such as xi prime equal qij t xj. Starting with a prime is qa q transpose. We have a bunch of equations where the last equation requires omega W equal Q transpose W prime Q plus Q transpose Q dot. For various choices of W satisfying the preceding condition, we obtain the corresponding objective stress rate sigma hat. In the German stress rate, W is selection rate. If we choose the rotation of the frame identical to the rotation R in the polar decomposition F equal VI, VR, we obtain W equal R dot R transpose, and the corresponding stress rate is known as Green-Marquis Nagidi stress rate. The Truesdale stress rate defined by sigma hat equals sigma dot minus nabla v dot sigma minus sigma dot nabla v transpose plus sigma nabla dot v, and the odroid stress rate defined by sigma hat equal sigma dot minus nabla v dot sigma minus sigma dot nabla v transpose are also well known in the literature as objective stress rate. Zhou and Tama have shown that the logarithmic spin rate W defined by the equation ddt log u minus w log u plus log u w equal d, where u is the right stretch tensor and d is the deformation rate, leads to an objective stress rate that has certain numerical advantages over other objective stress rate. I think we skip this above this part we skip. It's completely incomprehensible. So we move on to section 8.4, local conservation and balance laws. Local conservation and balance laws. The global conservation and balance laws presented in chapter 7 can be transformed into their local, global. This was global conservation and balance law. Now it's transformed into the local form or use of the stress tensors. We can use the Gauss theorem to achieve this transformation. The balance of energy will have to wait until we discuss some concepts from thermodynamics that Truesdale calls thermostatics. Conservation of mass, the global conservation equation. So this is something like this. Everything moves with time. This is just, if you go back to the material coordinate, you have something here. This whole thing. So in some later time, this will become, okay, this thing become funny shape like this, for example. But this material conserve. Okay. Or is this a mass? This is more like mass. This is mass. Mass conserves. This can be written as density. This is derivative of density. And what is this? This is what? From this, using this. How do you get this? Oh. How do you get this? dV should be like this one, right? dx, dy, dz, right? So, dV dot, this has to be like d dt dx d dt dy d dt dz. Is it correct? How do you get this? Let me try a different. Let me use a whiteboard. So we want to consider dv dot, right? dv dot, maybe this is like this. You can go limit. This is like limit delta t go to 0. Then you have v t plus delta t minus v t delta t. See, and this volume actually is a function of position. So v, this is x, it's complicated. It's more like dx, x is a function of time. So this is a t plus dt, then t plus dt minus v. This is also a position, which is time t, then t. I think this is the exact, more or less exact definition of this. Let me see. This is dt, dv, dv, dv. This dv. No, this is not, right? This is like, let's make d to, we can set d to delta v, delta v, delta v. Let me just keep d right? So then, what is this? d dt dv. This is more like this. You have to dv. See, I think you have to put v dotted with partial dv. This is volume. volume. This is volume, right? This is velocity. Then this plus partial t dv. So what is this? Partial I, partial v, partial I, partial I vi, partial I vi dv. What is this? This is partial x1 v1 plus partial x2 v2 plus partial x3 v3, right? Then we have this d I'm not sure how do you get this. Maybe I stop it. We can continue in the next video. I stop today. I stop here. Okay.